lesson of the year. We're going to get started off with some review, going quickly in with 3 sections here. Now remember that you will have to be taking notes for every section that we do. Today we're going to be starting off with this broad set of topics, which we will call properties of numbers and equations. So this is going to be properties of numbers and equations. Now I want to start you off by asking you a question. If a child came up to you and asked you what math is, what would you tell them? For me, what I would say is that math is a set of rules we use to try to describe problems. So what I would call this, and it's okay if you call it something different, is a set of rules to solve problems. Every piece of math that you will be seeing this year, somebody came up with because they were trying to figure out an answer to something. Now we're going to get started with something basic. This is something you've seen a couple of different times. This is the classification of numbers, or sets of numbers. We have a couple of different sets of numbers, and we're going to do these in a weird order, but we're going to start with the natural numbers. What are natural numbers? Natural numbers are counting numbers. So they're the numbers starting at 1, going to 2, 3, all the way up until infinity. Natural numbers are counting numbers. Next, we're going to go to whole numbers. Whole numbers are all of the natural numbers and 0. So what would be examples? Well, we would have 0, we would have 1, 2, all the way up until infinity. Next up, we have integers. And what are the integers? They're all the whole numbers and their negative counterparts. So the integers are all whole numbers and negative counterparts. What does this mean? Well, it means that we could have -3. We could have 0. We could have +3. And we could have any number up to infinity and any number down to -infinity. Next up, we're going to go to rational numbers. What are rational numbers? They're any numbers that can be expressed as a fraction. So a number like 1/2 or 1/2 would be a rational number. So would 0.75, because that's 3/4, but that could also be written as 75/100. This means that we could also have something like 324/577 and 86. But it means we could also have something like 1, because the number 1 is just 1 divided by 1. Any whole number like this, or any integer, is just itself divided by 1, or it's itself over 1. All right, what about irrational numbers? These are numbers that can't be put as fractions. The most famous example of an irrational number is pi. Pi is a number that can't be put as a fraction. Another way of saying they can't be put as a fraction is they're decimals that never repeat. Another one that's actually very famous is the square root of 2. If you put this into a calculator, you'll see you get 1.717, and it'll keep going. You won't see any of the numbers repeating. What about real numbers? Real numbers are any rational or irrational number. So a real number is any number that we have learned so far. We will deal a little bit later in the year with some numbers that aren't rational or irrational, but real numbers are anything. So a real number could be 0. It could be 7 over 6. It could be 3.754288, and that continues on. So these are our types of numbers. From smallest to largest, we start with the naturals, then we go to the whole numbers, then the integers, the rationals, irrationals, and all of those are real numbers. Now these actually work a little bit like a Venn diagram or Russian nesting dolls, right? If we're thinking about this, we could start off with something small like Ted the Beagle. Ted the Beagle is a type of beagle, but not all beagles are Ted. All beagles are also dogs, but again, not all dogs are beagles. All dogs are mammals, but not all mammals are dogs. Reptiles are just their own whole different section, but all of these are found on Earth. We can do the same thing with the numbers. At the very smallest, we have natural numbers. And then we said the next largest were the whole numbers. They were just the natural numbers and 0. What was the next largest? Well, integers were the next largest. Integers were all the whole numbers and the negatives. So integers are the next largest. And so what this means is that all natural numbers will also be whole numbers, right? 1, 2, 3, 4, those are all whole numbers. But not all whole numbers are natural, right? We have 0 out here. And all natural numbers will also be integers. 1 is an integer, 2 is an integer, and so on. So each of these are larger than the next. After this, we have the rational numbers. Rational numbers being all numbers that can be fractions. Any integer can be a fraction, can just be expressed as itself divided by 1. So negative 3 would be negative 3 over 1. 0 would be 0 over 1. Then we have the weird numbers, the irrationals. They're their own separate group off to the side. But all of these, all the rational, irrational, integers, whole numbers, and such, those are all real numbers. So remember that a real number could be irrational or it could be irrational. But all natural numbers will be real numbers. All whole numbers will be integers. All rational numbers will be real numbers. Great. Let's take a look at some practice with this. We're going to look at these numbers and try to figure out all the different sets or all the different types of numbers they are. So what is 5? Well, 5 is a counting number, so it's a natural. But 5 is also a couple more things, right? If it's a natural, that means we know it's also a whole number. If we know it's a whole number, we know it's also an integer. If we know it's an integer, we know it's also rational. And if it's rational, we know it's real. So the way to figure out which set these belong to is identify the smallest set it belongs to. What about negative 4? Is negative 4 a natural number? Is it 1 through infinity? No. Is it a whole number? Well, the whole numbers are just 0 through infinity, so it's not. Is it an integer? It is, because the integers are all the whole numbers and their negative counterparts. So this starts at an integer, and if it's an integer, we know it's rational, and we know it's real. What about this? We have a decimal here. Remember though, this decimal ends. that means it can be written as a fraction. This can be written as 3 and 285 over 1,000. So if this can be expressed as a fraction, what does that make that? That makes this rational. Now, is this a counting number or a negative counterpart of that? No, so this rational is the smallest group it's a part of. That also means that it's a real number. Right, 0, smallest group that belongs to is the whole numbers. Right, the whole numbers were all the counting numbers and 0. And if it's a whole, that means it's an integer, which means it's rational, which means it's real. What about the square root of 20? Well, the square root of any number that is not a perfect square, so the square root of anything that's not a perfect square, will be irrational. It will be a decimal that never ends. And if something's irrational, we know it's also real. And what about 5/3? Well, this is a fraction, meaning that we know the smallest thing it can be is rational, and we know that it must also be real. So now go ahead and do the first problem. We'll identify it, then we'll go on to the next one, identify it, the third one, identify it, and then the fourth one. Starting with this, -8. What type of number is this? -8 is a negative number, meaning the smallest thing it can be is an integer. But if it's an integer, that means we know it's also rational, and we know it's also real. What about the square root of 16? Here's a trick for this. Remember, the square root of 16 is equal to something. The square root of 16 is equal to 4, meaning that if it's 4, it's just like 5. It starts as a natural number. It's a counting number. It means it's a whole, which means it's an integer, and so on down the line. All right? What about 10/3? 10/3 is a fraction, meaning that the smallest thing it can be is rational. Only rationals or the reals can be fractions. If it's rational, that means it's also real. And the square root of 8? The square root of 8 is not a perfect square, meaning that this will be a decimal. This will end up being something like 2.567, and it'll keep going on. This is not a fraction. It's a non-repeating decimal, meaning that this will be irrational. But if something's irrational, that means it's also a real number. Great. Now let's look at trying to figure out what set of numbers best represents some of these situations. Let's talk about the number of holes you dig in the ground. So, how many holes can you dig in a ground? Well, you could have no holes dug, so you could have 0. But then when you start digging a hole, will you ever have half a hole? No, you would automatically have 1 hole. Or when you dig a second one, you'd have 2 holes. Or 3. So what does this look like? Well, we have 0, 1, 2, 3. No fractions, no decimals in between, and we start with 0. This would make it the whole numbers. What about the amount of money you're playing in $1 games of poker, and you can borrow money from a buddy if you run out, so you can go into debt? So how much money could you have? Well, you could have negative $70. Right? You owe your friend $70. You could have no money. You didn't make or lose anything. You could have $100. But if we're playing $1 hands of poker, can we have half a dollar? Can we have 50 cents? No. Meaning that we have negatives, we have 0, we have positive numbers, but we don't have any decimals or fractions. That would make this the integers. So this is it for your properties of numbers. Remember that we have all of those and they all stack onto each other. There's some really cool things that can be done with these a little bit later and a little bit higher in math. The next thing we're going to go on to is operations of numbers and properties of real numbers. First of all, what are operations that you can perform on numbers? Well, we have the four common ones, right? We have addition, we have subtraction, we have multiplication, and we have division. Now, for math terms, subtraction is actually just a fancy way of doing addition, and division is a fancy way of doing multiplication. So this means we can make properties for addition, and they'll apply to subtraction, and properties for multiplication that'll apply to division. Here are the important properties. The first is closure. What this means is that if we start with all of these being real numbers, then if you add two real numbers, the answer will be real. This is also true for multiplying. If you multiply two numbers together that are real, that means that the multiplied number will be real as well. What about commutative? Commutative means that we can do things in whatever order we want. So that means that if we add two numbers together, a and b, that's the same as adding b to a. So we can flip the order of what we're doing. This is also true of multiplication. If we're multiplying a into b, that's the same thing as multiplying b into a. Commutative means you can flip what you're doing. Associative is like who you associate with. So if you have two numbers that are best buds, and then they have a third number who just sort of hangs around. For math, which is not true in real life, that's the same thing as having the first friend be the one who's out of the loop, and your other two friends being best buds. So you can group numbers together when you're adding however you want. This is also true of multiplying. If you have two best buds who are hanging around, but sometimes they invite their third friend, that's the same thing as having the first friend be the one who's occasionally invited, and the other two multiply together. So you can multiply and you can add in whatever order you want. The next, we have an identity. And what this is saying is, what can we add or what can we multiply to a number to get it back to itself? Or in other words, a plus what number is equal to a? Well, what can you add to any number to make it itself? The answer is 0. This means that 0 is the additive identity. What about for multiplying? A times what will equal A? A times 1 will equal A, making 1 the multiplicative identity. And the inverses. So the inverses are, what do we do to make something come out to be the identity? Or in other words, A plus what will be equal to 0. So for adding, the inverse is negative A, right? If you have a negative version of a number, you add those together, that'll make 0. And this is why addition is the same as subtraction, because anytime you're adding, you can just have a negative number. What about for multiplication? A times, well, if we make a fraction or we divide by a, remember, fractions and dividing are the same, this will leave us with 1. Your a's will cancel out. So this is why multiplying is the same as division. And the last one we have is if you have distributing. So this means, how do these two systems interact? Well, if we have a plus b times c, right? So this is saying, what if we have 1 plus 2 and then we multiply them by 3? That's the same thing as doing the multiplication first and then adding. So adding, then multiplying is the same as multiplying, then adding. These are your properties of real numbers. What's really cool is there's sometimes that these don't all apply, but you learn about that in much higher math, so we're not going to cover that. All right, next let's move on to some terms. Hopefully you remember these. If not, this is your time for a refresher. What is a variable? A variable is a symbol typically a letter, so we'll say a letter that represents many numbers. So what are examples of a variable? Well, the common one in algebra is x, right? If we don't know what a number is, or it could be many things, it could be x. It could also be y, or it could be something like m in slope-intercept form. What's a numerical expression? A numerical expression is a math phrase that just has numbers and operators, or numbers and signs. So math with just numbers and signs. So this could be something like 3 times 1 plus 4. It could also be 2 minus 1 divided by 5. Okay, so what makes an algebraic expression different than a numerical expression? Well, an algebraic expression is just an expression again, but it can have variables as well. So this is going to be math with variables, numbers, and symbols. So this could be something like x plus 3, or 5 times x minus 7. Right, and what about like terms? Well, like terms are going to be terms. So terms are just small mathematical phrases, but they're terms with the same variables to the same power. So with same variables and the same power. So what would an example of like terms be? Well, it could be something like 3x and x. Or it could be 2xy squared and negative 5xy squared. Right? For both of these terms, we have x in its raised to the first power, and we have y in its raised to the second power. So that's what makes these like terms. Right. Now we're going to apply these and write out some expressions. We'll start with the first one. I'll go through it, and then I want you to try the next two on your own. If we have a truck that weighs 5,000 pounds and it's being loaded with 20-pound boxes, we're looking for the total weight. What would the total weight be? Well, that would be 5,000, right? We know there will be 5,000 pounds, and we have 20 pounds from each box. We just don't know how many boxes there are. There could be 1, there could be 100. So this would be how we write that expression. How do you write an expression for apples that cost 50 cents a piece and bananas that cost 20 cents a piece? Well, for this we would have 50 cents for each of the apples we buy. Could be 1, could be 1,000. And we have 20 cents for each banana we buy. Could be 3, could be 12, we just don't know. To make sure, we're also going to define our variables. So A would be our number of apples, and B would be our number of bananas. What about this one? We have 700 ounces of water in a bucket, and we're removing water using an 8-ounce cup. Well, we start with 700 ounces, but what are we doing? We are losing water, so we're going to subtract the water. And how much are we losing? Well, we're losing 8 ounces per cup. We don't know how many cups we've taken out, though. Could be 1, could be 2, could be 15. So C is going to be our number of cups. Finally, our last topic for this, talking about combining like terms or simplifying expressions. The rule for simplifying, remember that like goes with like. So like terms go with like terms. For example, with this, what are our like terms? What are our ones with the same variables and the same powers? We have 3x and we have negative 8x. So those two will combine. What's 3x minus 8x? Well, it's 3 minus 8 times x, or negative 5x plus 5y plus 7. What about this one? Well, we're going to need to distribute this in first. So we'll distribute that in. We get 6x minus 10x. Remember, the negative comes along for the ride. Minus 16 plus 4x. So now we need to look for the like terms. What are the terms with the same variables and the same powers? Well, we have 6x, we have 10x, and we have 4x. So we can combine these. This is 6 plus 4 minus 10. Or 6 plus 4 is 10 minus 10. So this is 0x minus 16 or minus 16. What about this one? We have 9a minus a. These are like terms, but what's our coefficient? What's the number in front of a here? Remember that that's just a 1. Anytime we just have a minus or a plus, it's a 1. So this is the same thing as 9 minus 1 times a, or 8a. Right. Now it's your guys' turn to try a couple of these. Go ahead and do this one. What is 8a plus 7b minus a plus 2b? Our like terms for this one are our a's and our b's. So what's 8 minus 1? That gives us 7a. What's 7 plus 2? That gives us 9 times b. Now let's go ahead and do this one. Remember, you're going to need to distribute this minus 1 in. So we start off by distributing that minus 1 in. We get 5x minus 7x. Remember, minus 1 times 7x minus 3 minus 8x. We have to distribute that negative in. What are we left with? Well, we have our x terms. And we can just look at the coefficients. So what's 5 minus 7 minus 18? 5 minus 7 will give us minus 2. Minus 8 gives us minus 10. So this is minus 10x minus 3. What about this one? The key for dealing with this one, we have both a decimal and a fraction. We want to make these two into the same thing. So let's try doing these as decimals, and then we'll try them as fractions. So we have 0.5n plus 3m. What's 3/4? Well, that's 0.75. So we have 0.5 minus 0.75. What does that leave us with? That leaves us with minus 0.25n, and then we didn't have anything to combine m with. What about if this were a fraction? Well, what's 0.5? That is 1 over 2. Right? It's 1/2. It's half of 1. So this is 1/2 n plus 3m minus 3 over 4ths n. Remember, when we're combining fractions, we need like denominators. So this would be the same thing as, we have to multiply this by 2 to make it into 4. This would be 2/4 n plus 3m minus 3/4 n. We subtract these, we would get minus 1/4 n plus 3m. Right, last one we have is here. Remember, you have to distribute the x in. So it'll end up multiplied to all of these. What happens when we distribute the x in? Well, we multiply this by x. What are we left with? Well, we have 3 times x times y. Plus, we have 5 times x. And then for this next one, we have 4 times x times y. So we get plus 4 times x times y minus 7 times x. So what are our like terms here? Well, we have 2 terms with both x and y, and 2 terms with just x. So we'll combine these. What's 3 plus 4? That gives us 7xy. And what's 5 minus 7? That'll give us minus 2x. And there you have it. This is our first lesson. Welcome back. I'm going to get started with the review, and you can go ahead and do your homework now.